Good morning, good afternoon, good evening, wherever you are. Thank you for joining me today. Today, I've got a real world use case to show you folks. It is a high concurrency and a low latency use case that one of my customers had. And I'll walk you through what that use case is and all the features of Dremio Sonar that helped be a big part in being a solution for this use case. All right, let's begin. Let's talk about what the customer was doing from a business standpoint first, right? And what we were helping them with, right? And then I'll get into the actual testing details. So, as part of the data lake platform initiative that they were building, the customer had a use case that needed to provide a dashboard with reporting and analytics to their end customers. They wanted this to allow them to query data that these end customers themselves have got. So it is more of an embedded service to their end customers, and the idea was to embed Dremio into the platform so that these end customers could have query capabilities, right? So what did this entail? Well, since the data sets themselves were owned by the end customers, they were completely custom, right? A lot of the queries were dynamic and impossible to predict beforehand, right? And since this was a multi-tenant use case, that means you had more than one end customer. As you would expect, one customer's data set would be drastically different from another, right? And also because one data set can be completely different from the other, the queries also were drastically different, right? In fact, the customers themselves did not have much idea about the data sets themselves, right? But they did have some idea about the data types and what was in the data set, right? As well as some ideas of the measures and the dimensions that could be used in a query. So these reports and dashboards were originally serviced by Elasticsearch, and what they told us is that this was becoming expensive and hard to maintain. And they started to build a data lake, and they had an ability to dump the data into Amazon S3 and use some query engine or the other to query the data, right? They were already using Trino for other use cases in the company. And after a quick proof of concept with Trino, they wondered if Trino was actually the right choice for them and if there was anything better, right? So they began evaluation of looking at Dremio to either replace or at least augment Trino. All right. So let's look at the proof of concept that they did with Dremio and Trino, right? This was a high concurrency and low latency use case for the proof of concept. They provided 1,700 queries initiated randomly at a rate of 30 queries per second. Now, keep in mind that this is 30 queries initiated per second, right? So imagine if a query took a few seconds to complete, then you can imagine that there will be potentially hundreds or thousands of queries initiated against Dremio or Trino at any given time, right? They provided about 160 different data sets from 160 different customers, right? And the overall data scan from a query perspective was about 40 gigabytes post any data pruning done by either Trino or Dremio, right? And the data format was in Parquet. Um, so looking at the results, we can see that Trino used about 20 workers with 16 cores and 64 gigs of memory. And there were 30 queries randomly selected from the set of 1,700 queries that they provided and initiated against Trino and Dremio for about 5 minutes at a rate of 30 queries per second, right? And then they measured a few things. They measured the median, which is TP50, as well as the TP95, right? So TP95 is essentially the 95th percentile. And what that means is it is essentially the max time of all the of a query of all the queries that were initiated, under which 95% of the queries have been completed, right? So for Trino, for example, it served 50% of the queries with the max time that a query took being 1.2 seconds, and for Dremio that was half a second. And the 95th percentile for Trino was about 5 seconds, and for Dremio was 3 seconds, right? And the key thing here is, if you notice, that Dremio did all of this with half the hardware to achieve these results, right? With Dremio using just 10 Dremio executors as opposed to Trino's 20 workers, right? This is actually a testament to Apache Arrow and the columnar execution that a query engine like Dremio can do using such a technology, right? So, what were the features in Dremio that enabled such an aggressive use case with lesser hardware? So one of the configuration options that you will be able to set in Dremio is a feature called Columnar Cloud Columnar Cache, or C3, right? C3 is an immensely useful feature for optimizing performance. It provides an opportunity to store locally on the Dremio executors the data that we fetch from the data lake storage, right? So this not only allows for faster initial reading, but also facilitates subsequent use for in later queries, right? And the reason this is important is because data lake storages like S3 can be highly variable in performance, right? Data lakes like S3 are, theoretically infinite in nature, but as a consequence, they are kind of slow, right? So by creating a cache on the executors, on the Dremio executors, where we store the data, we are, it kind of means that we can use that cache on the second, third, or fourth run of the query, right? It's also already right on the executors, so we don't need to spend time, refetching it from the data lake, right? Now, because C3 will be stored on the executors, it can be as fast as the disks you use to attach them to, right? So what that means is if you've got fast NVMe storage or SSD storage that can be attached to the executors, using C3 with these NVMe or SSD disk will vastly improve both the latency as well as the throughput, because we're actually going to read from these highly optimized storages, and we're not going to have to connect to the data lake to get the data. So when you have activated C3 correctly, you will actually see that it is, you can actually see in the Dremio query profile whether it's being used or not. All right, the next thing was data reflections, right? Reflections are a very unique way in Dremio, and one that separates Dremio from any other SQL query engine out there, right? They are the primary means of achieving performance that might not be achievable in any other way, right? So if there's a highly reusable query on a view, let's say that's got a complex join or something that takes a lot of processing power and resources, and if I got 100 users running that same logic over and over again, then it just kind of makes sense to just materialize that view, right? Why waste computing power for the same logic over and over again, right? The cool thing is that Dremio picks out the best reflection for your query automatically, and we do query rewrites, as opposed to the user keeping track of, hey, which materialized view to use, right? Dremio automatically rewrites your queries to basically pick out the best reflection for that query. And so if you're querying a data set in Dremio, which is accelerated by a reflection, then Dremio does not need to retrieve any data from the original sources and will instead retrieve the data to fulfill the query from the reflection store instead, right? One of the things that is important to note about reflections is that we have the ability to effectively use a reflection that doesn't necessarily need to cover the whole query, right? So in this case, we might get some of the results from the reflection, and the remaining data can be retrieved from the original sources, right? There are a few different types of reflections. There's raw reflections, aggregate reflections, and external reflections. I won't get into the details in this session, though. You can find more information about them on our website. For our customer use case, though, we could not use reflections because of the dynamic nature of the queries in the data sets, because there was no way to know the queries beforehand to turn on a reflection. But if we could have turned them on, we believe we could have achieved much better results than what we got, right? Again, this proof of concept that we did was a testament to the raw power of Apache Arrow, right? And the columnar execution that we can do against that. All right, Elastic Engines, right? Elastic Engines are a way that Dremio organizes executors into different pools called engines, right? And you can match them to different workloads, right? Along with Elastic Engines, Dremio has provided something known as a workload management capabilities, which is often referred to as WLM, which route queries to an engine that you can choose, right? So in this diagram, we have a variety of queries that first arrive on an incoming job queue. Uh, these queries are then distributed to the engine that they should run on based on the rules that you define, right? So with WLM, you can make decisions not only on how many queues are there, but also how the queues are mapped to engines, which gives you the ability to basically dictate how many CPU resources and what priority you want to set for the various workloads, right? So what essentially you're doing is you're creating individual sub-clusters that are isolated in terms of resources, and they can be dedicated to workloads, right? And this in effect prevents the noisy neighbor problem, right? And this was huge to achieve what we did in the POC, right? And this is something that I noticed that many of my customers don't take use of, right? Sometimes they do everything on a single 10-node cluster. Even when a small split of the cluster into multiple engines, say, for example, one engine of 7 nodes and another engine of 3 nodes, would drastically reduce the noisy neighbor problem and could achieve better performance, right? Here's how to use WLM, right? WLM or workload management consists of a variety of rules that are evaluated one at a time in a priority order, right? So here in this first diagram, you see you start at rule 1. If rule 1 is matched, then the query will be placed into an associated queue or allocated to a particular engine. Here it's called the queue 1. If rule 1 is not matched, then Dremio proceeds to evaluate rule 2. And if rule 2 is matched, and then the query will be allocated to queue 2 and so on, right? As you may know, queries can be sent to Dremio from a variety of sources, such as JDBC clients or ODBC clients, Arrowflight clients, or via the REST API, etc. Right? And you can track, and Dremio keeps a track of where these queries come from, and you can use that you can use the information to create the rules, right? You can also use query cost. And this was key in our POC because since we did not know what type of queries were being initiated or the query cost or what the complexity involved, what we did is we routed the more costly queries to a larger engine, right, and the smaller queries to a smaller engine, right? And you could also control how much memory, right, basically the memory footprint and the CPU scheduling of your queries, right? You can limit your queues based on things like queue time, runtime, memory use per node. You can control the CPU priority of your queues, right? All of this were used to support this high concurrency use case, right? So if you're not using WLM today, please make sure you use them. Even simple engines or simple splits of the cluster can help reduce the noisy neighbor problem in such high concurrency use cases. Right. Another useful thing to understand is how Dremio does planning of a query, right? So when a user submits a query, the Dremio optimizer and the query planner goes through several steps prior to executing it, right? The first thing it does is goes through a parsing phase, and we convert the query into a relational algebraic representation. And then we do this in an iterative manner, right? We go through an iterative planning phase. We identify if there are any reflections that are used capable of covering that query, as well as basically planning out and seeing what the query would look like even without reflections, right? The query planner will essentially generate a query plan and produce cost estimates for a plan, and ultimately it'll pick out the lowest cost plan from all the plans that it has generated, right? And all of this processing is essentially done on the coordinator node, right? Once we arrive at the most optimized plan, it is then submitted to the executors to be executed, right? And all this happens in a few milliseconds or so, right? The cool thing is in Dremio, we have a feature that's called query plan cache that can cache these query plans, right? So the query plan cache is useful because when we plan the query for very first time, we'll put the most optimal plan into the cache. And if the same query or a similar query is submitted again, Dremio will search the cache to see, hey, if the plan has already been generated, and we can then use a cached version of it, right? This will save, this will kind of save relatively a large portion of a potentially expensive planning time, right? In the query profile of a job, you will be notified if the query plan was taken from the query plan cache or not, right? So you can identify whether queries are using it or not. All right. Another feature that we have introduced into Dremio is runtime filtering, right? This is a feature that can optimize situations where you are performing a join between a large fact table and a small dimension table, right? So the diagram on the screen tries to describe the purpose and the benefits of runtime filtering, right? Let's consider the top diagram first, right? Here we have a large fact table, and if you're going to join it with a smaller dimension table, you use a specific filter condition, right? So without runtime filtering, Dremio will need to read the contents of the entire fact table, as well as it needs to read the entire contents of the dimension table. It will try to perform the join in memory, and then it will filter out the records that did not match the filter criteria. The bottom diagram tries to depict what will happen if we do have runtime filter enabled, right? So in this scenario, the table reads begin in parallel again. However, as soon as the records are retrieved from the dimension table, the distinct join keys are pushed as a filter into the threads retrieving the data from the large fact table. So we only need to read the relevant data out of the fact table that's required to complete the join, right? And this can be vastly less data to return that can be returned to Dremio to process, right? And this can, really improve query performance, right? All right, and the last feature that was relevant was Arrowflight. I won't go into much details about this. There are other incredible sessions in Subsurface that you can attend to learn more about this. This is also available on the Apache Arrow website as well as the Dremio website. They are all relevant sources for this. But at a very high level, right? Arrowflight is a high-performance way to transfer data, right? And since everything in Dremio is done using the Apache Arrow memory format, right, we can transfer those arrow buffers directly to a client without converting into another format, right? And since it's built on gRPC, it's pretty fast, it's multi-threaded, as opposed to something like ODBC or JDBC, right? And this is instrumental for many extraction use cases, right? So if you want to transfer data to a client, and let's say you have, I don't know, a data scientist use case, for example, right? A machine learning use case, right? A data scientist may need to extract 100 million or 200 million rows or something like to go build a machine learning model, right? So instead of waiting around for a single-threaded ODBC extraction job, a multi-threaded Arrowflight extraction job can improve your productive drastically, right? All right. So these were all the features that that is relevant to our proof of concept that we did with this customer, and what was used to achieve such high performance.